This video is a sample problem based on reality, all right, where FM, the original FM, was modified to include stereo. Okay, that was one of the cool things about FM originally was AM was mono, FM had the capability for stereo. All right, so think of it this way. Think of us having two signals, a left and a right, M1 and M2. All right, so here's a block diagram that shows how you would reconstruct the message signal S of t. Maybe I should call it SM of t because it's the thing that's going to get modulated by an FM modulator, but it uses AM kind of methods to form that signal. All right, so a couple of things here that we haven't talked about. We haven't talked about this block called, all right, so let me point to it, this block called frequency times 2. All right, so we'll get to that, but for now, think of it as I have an input here that's a 19 kilohertz oscillator. I put it into this circuit, and out comes another oscillator, but the frequency of that oscillator is multiplied by 2. Okay, so we'll talk about how that would work at the end of this video. Okay, so from here, this is what I'd want you to be able to do on an exam. If I gave you this problem, I would want you to look at the way this block diagram is constructed, and I notice that X of t has, first of all, let's put a little check mark here, it's got M1 of t. All right, so let's put that down, M1 of t. And then we have here M2 multiplied by the oscillator. Okay, so that gets added in at this end of the summer. So here we go, M2 cosine 2 pi 38 kt. All right, so that forms X, and then what we have for SM is X of t plus, well, we also have, here's X of t, then on this side we have also the 19 kilohertz carrier. All right, so plus cosine 2 pi 19 kt. All right, so let's take a look at SM and look at what it looks like in the frequency domain. Okay, so I can expand that a little bit, SM of t. So this would be, a question. Find the magnitude S, that's capital S, M of F, the Fourier transform of this stereo message signal. Okay, so SM of t is going to be M1 of t plus M2 of t, I forgot the of t up here, cosine 2 pi 38 kt plus cosine 2 pi 19 kt. All right, these are things that we can take the Fourier transform of, and we take a look here at the shapes. M1 is the triangle shape, and M2 is the adjacent wedges shape. So when I look at this transform, this first block here in green would just be the triangle shape. Okay, and we know its maximum bandwidth is 2 pi 15k, so let's just make this on the f-axis. So that'd be 15k. All right, so the green shape. All right, next let's take a look at the oscillator. Okay, we think, well, an oscillator, that's spikes. All right, so that should show up at 19k and minus 19K. All right. And then finally, let's switch to a different color. Let's go blue. This term, M2, that's the adjacent wedges. Okay. That would be centered at 38K. All right. So 19 times 2. All right. We'd have this. And so, getting the scale approximately right. It's not exactly right, but I would have these wedges. Okay, this is 38K. All right, so 38 minus 15 would give me 23K. And 38 plus 15 would give me 53K hertz. All right, and so I'd have that both plus and minus, right? Because a modulated signal gets sent forward in frequency and backwards in frequency. All right, so there is my shape for M2. Okay, so all of this is SM of F, and I've kind of been loose with the amplitudes. You could fix that up and make the amplitudes show up in your sketch as well. All right, so that's what that looks like. Okay, so the brilliance of this is that by doing it this way, we are actually transmitting an oscillator that can be recovered from SM of F. All right, so for example, if I put SM of T in here, and then I made a narrow band pass filter centered at 19K hertz.
Even President Nixon
what's going to show
allowed senior officials to testify under oath. Not only did he allow...
Sorry, my computer just fired off. This bandpass filter is just going to select this one, these two terms at 19K. All right, so coming out of here, coming out of the bandpass filter that's centered at 19K, so think of it this way, bump, bump. Then what we get is an oscillator. Okay, so I'll just call that O of T, and that would be proportional to some constant alpha times cosine 2 pi 19kt. All right, so from there we could also take SM and we could do low pass filtering with a bandwidth equal to 15K. And you see, if I did that, I would recover the message signal, M1. Okay? And then finally, if I take SM of T and I multiply it by my oscillator signal, so tapping off here and putting that here, O of T, and then I low pass filter with a bandwidth equal to 15K. What can you envision happening here? Well, wouldn't it be that this term gets copied? Okay, and since we're multiplying by 19K, this would move it down from oh, I'm sorry, it's not 19K. You need the frequency multiplied by 2 again. So you need to change this. You do this bandpass filter. Let me modify this. Okay. So you take O of T, put it into here, frequency multiplied by 2, and that gives you the 38K. So the 38K gets moved down from 38K back down to baseband. So you can imagine how that would work. All right, so from 38K, this gets moved down back to 0. We low pass filter, and now it comes M2 of T. Okay, so the brilliance here is that by transmitting the carrier frequency with the message signal, we can decode. We can do synchronous, AM DSB suppress carrier. We can use that technique to recover both M1 and M2. Okay, and then I think in the original FM receivers, if you wanted to have stereo, you could have a little LED hooked up to this pilot tone. They called that a pilot tone. Okay, and so when stereo was coming in, you would detect that pilot tone, and it would light up an LED, and it would show that you're getting stereo FM. Okay, so we've gone quite a bit with this. I wanted to finally conclude this video by explaining this frequency times 2 block. All right, how would you do that? Okay, so the idea is we're putting in an oscillator with a certain 2 pi f naught t, and we were getting out something that's twice the frequency. Okay, so 2 f naught t. All right, so consider the following. What if we took an oscillator, okay, and we put it into a square law kind of device? All right, so there's all kinds of circuits you can build that have nonlinearities that would give you an input-output transfer function that looks something like this, something like squaring. It doesn't actually have to be perfectly squaring, it's just some kind of nonlinearity. All right, so if I took cosine 2 pi f naught t and I squared it, out here would be cosine squared 2 pi f naught t, and then I know from there I would have a trig identity that shows that this is 1/2 cosine 4 pi f naught t divided by 2, which of course is exactly what I'm wanting in this frequency multiplier. So I then just follow this up, so I'm going to move this math up to here. Follow this up with a little bandpass filter, all right, to just keep this term and get rid of the DC term. Okay, so out would come the frequency multiplier by frequency multiplied by 2. All right, so the advantage of that is that the frequency and the phase between input and output would match exactly. You're not resynthesizing another oscillator from a circuit, and so those parameters would match exactly because one is derived from the other. All right, so lots to think about there. Hopefully you find this interesting and useful.